So in the last lecture, we learned about entropy, and also we defined this graph homomorphism. So homomorphism GH is the number of homomorphism from G to H, which is a function on vertices so that the adjacency are preserved. And so before we write in G to H, because we fix H and we vary G, right? Now what we want to do is we want to fix H and vary G. So we will write it this way. So this, homomorphism has some, applications once we consider this or this. So for this, we dealt with two instances of counting independent set or counting proper coloring, But now we want to focus more on this. So you have a fixed graph H and you want to embed into, you want to map it into G in a homomorphic way. So let's say T of G, HG with the number of homomorphisms divided by the number of vertices in G to the number of vertices in H be the homomorphism density of H in G. In other words, so if you consider this term, this is all possible maps from H to G. We count all possible maps, then that's the bottom. So this is actually the probability that a map from vertices of H to vertices of G, which is chosen uniformly at random, actually yields a graph homomorphism. So out of all possible maps, you only count the graph homomorphism. So this is graph homomorphism density. So measuring this is same as counting the number of homomorphisms because we automatically know the bottom here. So regarding the problem of counting homomorphism, one of the famous conjecture is by Sidorenko, which is called Sidorenko's conjecture. If H is a bipartite graph, then for any G, we have the homomorphism density from H to G is at least this. So this is actually H density. K2 to G, you have to map these two into the edges, but there are two ways, one to A, B, then one to A and one to B, or one to B, one to A. So T of K2 G is nothing but 2 times number of edges and number of vertices in G square. So this is a probability that you just randomly map an edge into G, then probability that it actually maps into G. So this is a part that so this is one edge, and this H could be a collection of edges tied together, right? This basically is the probability that you map one edge at random and one edge at random, one edge at random, without any interference between them, that's the probability that all the edges are mapped into an edge in G. So you forget the structure of H at all. Then, having a structure in H, if H is a bipartite graph, the having a structure, so these edges tied together in a bipartite way, only makes it easier to actually embed into G in a homomorphic way. That's what roughly this conjecture says. Or another way is that this is actually the number of homomorphism, which is G and P, where P is T, K2, G. Yeah. So if you consider random graph, so in random graph, if you embed H, then you embed it, you take the vertex map, the probability that it's here, it's here, it's H is here, H is here are P. Then you can compute that this and this are same. So what is another interpretation of this is that among the all graph G, the one that has the least number of homomorphism, H homomorphism, is the random graph. So that's two interpretation. Give me a moment. Okay, so and yeah, this conjecture is wide open. Some instance of H, for some instance of H, it is known to be true. And for example, if H is not bipartite, then this is not true. For example, if you take a triangle as H, and G is a complete bipartite graph, then the left-hand side is 0, while the right-hand side is quite high. So being bipartite here is actually necessary. Anyway, in my understanding, current belief of the people is that it is true if H has many symmetry, but otherwise it might not be true, as this is quite a strong conjecture. Yeah. So, in my understanding, many people believe that it might not be true. Anyway, so we can actually prove some graphs satisfy this Lancose conjecture. So, for example, if H is a tree, then for any G, we have the number of homomorphism, H homomorphism density is at least the labeled H density to the E of H. So let's prove this. So this is a proof by Colon, Kim, Lee. So let T be a tree, and we fix some ordering. So what we want to do is we want to use entropy to count the number of homomorphism. And for that, what we have to do is we have to give a probability distribution on the homomorphism set from HT to G. So giving a probability distribution is same as coming up of a way of generating a homomorphism in a random way. So we will introduce an algorithm which generates a T homomorphism in G with a certain probability. So it's a random algorithm. So let T be a tree with fixed ordering. Let's say x0 is a root, x1 to say xt. Let's say T has a xt edges, where each xi has an earlier neighbor. So let's say such an ordering is an appropriate ordering. So we know that we can order it this way. What you do is you take a tree and you take a leaf and delete, leaf and delete, leaf and delete, and then you write down the vertices in the reverse order that you deleted. The one that's deleted later is at the beginning, and the one you deleted earlier is at the end. Then this satisfies such property. Now we consider the following T branching random walk on, say, n vertex graph G. So if you see here, you will see what we want to do. So we want to come up with an algorithm to find the H homomorphism, T homomorphism inside of G. But in G, we have edges. We want to make sure that what here is the probability that H is embedded in G. So that's, in order to get some terms like this, we want the edges here to be chosen to be mapped by edges in here in a uniform way. So what we want to ensure is that for edge here, it will map to some edge here. We want this image of this edge is a uniform edge in G. So all the edges here, the probability that this is an image of this is same as the other edge is an image of this. So that's what we want to make sure. So we want to come up with an algorithm which have this property. So how do we ensure? We choose V0 in, let's say we want to map pi so that the x0 to xt are mapped to v0 to vt. So vi denotes the image of xi. So we choose v0 in as a vertex in G with a probability degree of v0 over 2 times number of edges. So we know that summation of degree is exactly 2 times number of edges. So this gives us the probability distribution of this one vertex. And if you add the probability on all the vertices, then that adds up to 1. So this is actually probability distribution. This is called stationary distribution. And step 2. Assume we have embedded v0 to vi minus 1. Then let xj be the unique earlier neighbor of xi. So we are about to embed, say we have determined So we have embedded x0 to xi minus 1 and we are about to embed xi. And let xj be the unique earlier neighbor of xi. Then we choose vi from, so we want to make sure that vi is a neighbor of bj. But we choose uniformly at random from neighborhood of bj. And step 3, we repeat step 2 until the end. So this obviously gives you one copy of homomorphism from T to G, because every time you make sure that you choose Vi from neighborhood Vj. So Vi and Vj should be adjacent. So you always get a graph homomorphism. So with a certain probability, because all the procedures are random, so this gives us a distribution on the set of all homomorphisms from T to G. So if you see, you can see why we choose it this way. If you consider V0 and V1, no, X0 and X1, this edge, see where does it map to? For specific edge, say UV, the probability that this maps to U and this maps to B is what? This maps to here with the probability D of U over 2EH. And probability that this maps to B is 1 over degree U, because you have several neighbors and one of them is this, so you choose uniformly random where to embed x1, so this is this. This is 1 over 2 E of H. So, and of course the probability that this is mapped to B and this is mapped to B, U is also 1 over 2 EH. So there are E of H edges and there are two ways for this to be embedded. So all those ways are equally likely. And this is true for x0 and x1, but we also want to make sure that this is true for other edges in T as well. So that's why we want to prove one. That's one thing that we want to prove. And another thing we want to prove is that when we have T prime, so we have a leaf L, and less of them is T prime, and we have leaf, then entire thing is T. Then, here, what does it say? If we have a 3T prime G, then if we know, so we want to use some induction. If we know this, and then we want to make sure that, this holds, then this is nothing but just plus 1, right? So we want to make sure that here, what we want to make sure that is that using this algorithm, if you embed this first, and then you add this, then this addition is also done in a uniform way, so that you multiply, correct number, which is this. So we have to check two things. Edges of T are mapped into edges of G in a uniform way. And we can kind of restrict our situation of T into T prime. Then we are in a good shape to apply induction. So let pi be the resulting homomorphism. So this is random variable. Then for a specific homomorphism, what's the probability that our random homomorphism is same as this specific one? So first, the x0 has to be mapped to v0, which happens with exactly this probability. You have to choose v0 at the beginning. And you choose x1 with this many choices. So x0, x1. Oh, sorry, this is v0. And x2 is say 1 over degree of b1 way, and x3 is again 1 over degree of gb0 way. So out of these choices, we have to choose b3, which is that, and so on. We kept multiplying. But how many these terms? So you see, this and this term are same because x2 is chosen from neighbor of x1 and x3 is chosen from neighbor of x0. Actually, this x3 could be same as this. So no, I said it wrong. So x3. So b3 could be same as b1. So it doesn't matter. You don't have to avoid the collision. So this is again exactly same term. But how many times this occurs? Exactly the number of neighbors of b0, x7, x9. Then when we embed this to, b7 or b9, we choose one of the neighbors of the b0. So this is actually multiplied by exactly the degree of x0 times here. And again, how many times do we multiply other term, this term? When we choose this, we multiply. When you choose this, we multiply. But when you choose, so this is already given. So for this, it's actually one less. By the same logic, for all other vertices, you actually multiply this as a degree of xi minus 1. But because of this one additional term, what you get is 1 over 2e of g, 1 over degree of g, b0, dt x0, minus 1. So you can write everything in one way, that I is from 0 to t. You take 1 over degree of bi to the degree of xi minus 1. So for specific points, the probability distribution that we gave, the probability that this is chosen can be written in this way. Exactly, we know the formula. But here, one noticeable thing is that this is only depending on degree of b in g and degree of x in t. The ordering of t does not matter. The ordering of bt, which is x0, x1, xt. We embed this first and then this, that was the ordering, right? But if you take another appropriate ordering and you do the computation, then you get the exactly same thing. So this algorithm actually puts the vertices one by one, but the final distribution you get, final probability distribution you get, is irrelevant of the ordering. Then what it means? So if we have a t and we want to show that this specific edge xi and xj are mapping into g in a uniform way, then what we do is we simply choose the ordering such that this is the root x0 and this is x1. You can actually find the ordering. This is x0, x1, and then rest of them are listed in an appropriate way, that it has one earlier neighbor. You can do that. That's an easy fact in graph theory. You can prove it by yourself. Then, because of the previous observation that we have deleted it, because of this first step and then second step, you can actually see that this is mapped to this, probability that this is mapped to here and the probability that this is mapped to here are same. So distribution stays same even if we change the ordering. So for each xy in H and uv in G, the probability that x is mapped to u and y is mapped to b is exactly 1 over 2e of g. So that's what we get. So we collect this one fact. And let's say t prime is t minus L a leaf. Then let's say p prime is a random homomorphism obtained by t which is a homomorphism from T prime to G obtained by random T prime branching random walk. So T prime branching random walk is, you consider this algorithm for T prime. Then what we have is that you consider an ordering where this L comes last, and you do the above algorithm for T, but you stop it right before you actually embed L. Then that's exactly same as a T prime branching random walk. So T prime branching random walk is nothing but the T branching random walk modulo the last vertex out, modulo L out. So this can be actually, written that for any P prime which is homomorphism of T prime G, this is actually summation of all the probability that the T branching random walk is same with psi, where psi restricted to BP is same as psi prime. So this formula is what I just said. You do this random branching work for T, and then you stop it right before the end, so you don't care what happens at the last vertex. Then that's exactly same as T prime random branching work. Then pi restricted to T prime, and this pi prime has the same distribution. So now we can prove we have collected all the elements that we want to show. So we want to show that for a tree with T edges, and let's say pi sub T is chosen from all the homomorphism from T and G, which is obtained by the above probability distribution. T branching random walk. Then we have what? Entropy of this pi t. So again, pi t is a random variable, so it has an entropy. This is at least t times log of number of edges in G minus t minus 1 times log of n. So this is what we want to prove. So once we prove, then it's easy to actually finish the proof. So we will do it after proof. So if t is 1, it's trivial. And we want to use induction. Assume the statement holds for t prime, which is t minus L, where L is a leaf. In other words, not in other words. Anyway, by induction hypothesis, what we have? Entropy of this P pi t prime is at least t minus 1 times log of twice of number of edges in G minus t minus 2 times log of n. So let B0, B1, and Bt be the appropriate ordering where L is the last one. And say Bt is adjacent to, let's use x0, x1 to xt. No, okay, let's, yeah. And xt is adjacent to xj. Then what we have? the entropy of phi t is entropy of phi restricted to t prime plus the last element, say vt, vi is say pi of xi, which is also a random variable, assuming we have this restriction. This and this may be a bit confusing, but let's put parentheses then. Then, what is this? This is nothing but, as we've seen before, it's same as phi sub t prime. And here, assuming this is given, now we have this. But this actually is related to only Vj. So this is actually same as information we get when Vj is given, the amount of information we get from Vt. I mean, if you want to prove this in a more rigorous way, I mean, you can actually, write this as by the formula, which is given by the definition, and you collect all the pi, all this pi, which has the same Vj on the same term, and you group them depending on the image of this on here, and then you write this, and then you take the whole image of this with a fixed Vj into one term, and then you suppress it, and you can actually get the formula, which is definition of this. But intuitively, Vt is only depending on Vj because we choose Vt from the neighbor of Vj. We take Vj and we take its neighborhood. We choose one of them at random. That's Vt, right? That's the exactly definition of Vt. So, no matter what other information is given in here, that is irrelevant as long as we have Vj, information of Vj. Then what's this? And by using the chain rule, this is nothing but you take the joint distribution and you subtract Vj. But what's this? By the induction hypothesis, this is that. And what's this? Vj, Vt. So this is xj, xt is an h. And this is the image of this. Where does it map to? But what do we prove? We prove that this. So this is uniformly chosen from all the edges in EG. So uniform case, this is a uniform distribution among all the edges of G. So this is nothing but the entropy is nothing but this. So this is uniformly chosen labeled edge. So 2 times E of G, and you take the log. And what's this? This is choosing Vj from vertices of Vg. But we know that entropy of X is at most log 2 of the S, where S is a possible value that X can take. So we don't know whether, we don't care whether, how this is distributed. It's actually distributed with respect to this stationary distribution, because order doesn't matter if we choose that vertex at the beginning and embed, and this is the distribution. But this is maximized when it's uniform. So there is minus, so you can get the maximum here. Then what's this? This is nothing but t log 2 E of G minus t minus 1 log 2n, which is exactly what we wanted to prove. So by induction, the claim is finished. Then what do we know? We know that t times log 2 times E of G minus t minus 1 log sub 2n is lower bound of this entropy of t phi And we know that this is at most, I mean, the number of homomorphisms taking log. Because, I mean, this is a distribution over this. It may not be uniform, but it's maximized. The entropy is not bigger than the uniform entropy over there. You have this now. So from here, you take the exponential, then 2 to the t log 2eg minus t minus 1 log 2n, which is 2eg to the n to the t minus 1, which is n to the 2t n to the t plus 1, which is k2 k, which is the t2 t sub, homomorphism density of k2 of g to the t and to the t minus 1. You divide it by n to the t minus 1, then this is bigger than that, which is exactly t of tg is at least t of k2 gt. So this proves the Lancose conjecture when h is 3. Yes. So now we conclude this section, and in next video we will learn more about independent sets. Before we show that the number of independent sets in a regular bipartite graph is maximized when it's disjoint union of complete bipartite graph, KDD. And now we want to show that for possibly non-bipartite graph. So we consider all deregular graph and what's the maximum number of independent set. And before doing that, we also want to consider the size of largest independent set or size of average size of independent set in some given graph. So we also prove some theorem about that in the next video. Probably in the next video we cannot finish it, but we will keep do that on the next lecture as well.